thank you for this opportunity to present my work and describe what I think is very interesting things to you. So I took the idea that it should be a chalk talk seriously, so it is actually not slides. You know, we're probably going to turn this off. And I prepared a lecture for you that is mostly a chalk lecture. All right, so my name is Alex Morozov, and I'm in the physics department at Rutgers University in the US. And I would like to describe to you something that you may not have thought about, but hopefully I can convince you that this is an interesting problem. So you probably heard about networks, right? Everything is a network. Your Facebook friends, you know, friends of friends and so on make a network. Sequences and mutations between sequences are networks. So let's consider a network which has n nodes. So it's really important for you to see what I write, because it's really 95% of what I'm going to present. And so tell me if there's like not enough light or you have trouble seeing it. So
is it possible to turn that light on?
Yes. I mean, it would be. It is on, and I'm not sure if it could be turned up.
I don't know. I think you want to turn this light up?
Yeah, to see the shot look better.
I don't know.
It is on already.
Okay.
Yeah. Yes, I noticed yesterday that it's a little dark, just sitting sort of in the middle. So in the meantime, so we don't waste time, I'll draw my network. Is it better? Okay, perfect. Yeah. Now it's blinding me when I look at it, but that's okay. I'll survive. Okay, so this is something like a generic network with n nodes, and let's say this node is I, and this node is j. And first thing I want to define is a weight on each edge. So you can jump from I to j, as indicated by this line. And I want to assign a weight to it. Okay, so and the weight for unweighted network would be just 1. Right? It's not a probability, it's a weight, so it would be 1 here, and 1 over there. All right? So next thing that you want to define is jump probabilities, right? So I gave you weights, but I haven't normalized them. So that's easy to do. So this sum is over all nearest neighbors. And what I do, if all of these weights are 1, 1, and 1, then the jump probabilities are going to be 1/3, 1/3, 1/3, just because I divided by the sum. Okay, so we will focus in this talk on the system with symmetric weights. So I defined omega ji, and that's going to be equal to omega ij. Okay, and the reason for it will become clearer later. Basically, the math does not go through unless you do this, some of the math. So the last thing that I want to define in the way of introduction is P sub I. So what we will be doing is we'll be doing a random walk on this network, right? So far it's just the network itself, but let's say I start from here and I walk around. I could have an ensemble of random walkers, which means that I walk according to this probability, right, the jump probabilities, and then they will settle into some sort of equilibrium, right, after a while. And these probabilities, equilibrium or non-equilibrium, I will define pi sub I. So sorry, this is supposed to be pi. So this could be an equilibrium or non-equilibrium probability for the walker to be at node I. Okay, pi sub I. Okay, so here's the system. So you can start from somewhere, let's say a single random walker, and walk around. You can settle into an equilibrium where you visit any node many times, or you could do a short random walk. So this is sort of the kind of a system. So you can write an equation which is called the master equation, and which describes this random walk. So this is discrete time. So let's imagine that you make a decision according to the jump probabilities from t to t plus 1, and then t plus 2, t plus 3, and so on. And you may have seen this type of equation. This is a gain term. That's what comes into the node, right? And this is the loss term. That's what jumps out of the node. You can imagine an ensemble of random walkers, and they sort of jump in and out. And I'm focusing on node I. And what I will do for now, I will say that this is the sum of probabilities to jump out. And I will say that this is 1, so you are forced to jump out. Okay, so this is a hallmark of simple random walks. So you could have imagined a slightly different system where you wait for a while and then jump. So this one is not like this. You are forced to jump according to the links that you have. Like if this is 1/3, 1/3, 1/3, and an unweighted network, then you make a jump into one of these three. Okay, so now if the weights are symmetric, if this is true, you can argue. So first of all, you can focus on steady state. So this is 0 at steady state. So then this is 1, so pi I is equal to this sum. And if you look at it a little bit more closely, you will see that this is completely standard, so I'm omitting a couple of details. But you will see that if I set this to 0 and I set this to 1, so this is my equation, pi I is equal to this sum over j, okay? Then I can solve this. So this is at steady state now, where where omega sub I is going to be something that we will call the total outward rate. It already showed up in here. This is omega sub I. So this is the sum of all omega ji, the edge weights. And the sum is over all neighbors of node, nearest neighbors of node I. Okay? So fine. This is completely standard and just sort of serves in a way of an introduction. The idea of my talk is to gain information about a network when the network is large and you don't know what it is. So this is where it's going to. So suppose you have a small network with 100 nodes, then you can always compute all of its statistics because it's on your computer, right? But sometimes you don't. You have the liberty to go from node to node and ask what the node is doing. For example, I come to somebody on the street and I ask, okay, are you a smoker or not? So, and then I write down 0 or 1. And then I ask, who are your friends? And then he tells me, and then I go to one of those persons, randomly. And then I just do the same. And I do this for, let's say, 1,000 people, 1,000 times I try this. Can I, for example, estimate, if I do this in Paris, can I estimate the fraction of smokers or the total number of smokers in Paris on the basis of a small sample? So this is where I'm going at with this. And we need an eraser to proceed. So far for this kind of question, this is useless, because once you start talking about steady state, that means you have to ask everybody many times to settle into a steady state or an equilibrium. So far I haven't told you how to do this. But let's say that we divide the network into subsets. So we don't know the size of the subsets, but we know that all the population of Paris is smokers or non-smokers. Okay, so that would be 2 subsets. And then nx, because n is the total number, is then total number of nodes in a subset. With property x. Okay, so this could be your total number of smokers, right? And then x would be a smoker, 1, 0, non-smoker. Okay, it could be anything you want. If it's a continuous property, you have to bin it. So by definition, they sum up to 1. And then you can always divide your system into your subset of interest that you don't know the properties of and that you want to infer on the basis of a short random walk and the complement. Right? So they're always like smokers and non-smokers in your data set. It could be more than 2. So now I will show you, unfortunately, I have a 16-page write-up here and I only have an hour and a half. So I'll have to skip an interesting derivation and just proceed to a result that's not due to me, but due to a famous physicist called Katz, K-A-C, who worked on path integrals and things like this. So if I introduce a probability that a random walker, RW is a random walker, reaches a node in Sx, and Sx is the set that consists of nx nodes. So all the nodes of which there is nx, the total number, will be a set I will call Sx. After L steps, okay, so this is the so-called first passage probability. So you start somewhere that's not an Sx. So it's a very simple system, really. You start somewhere that's not where you want to be. And you mark the nodes as targets for you know, the nodes that you want to be in. In this particular example, it's the nodes with property x that belong to this set. And then you just run your random walk, and once you get to the node with property x, you stop, and then you can record the number of steps it took, right? For example, just to make an example on the fly, for example, I want to be, so this belongs to Sx. Let's say it's the only one that belongs there, and I can start here. So I can walk here, and let's say this is the whole network. So I can walk here by chance, then I have to come back because there's nothing else, and then by chance I get there. All right, so this is L equals 3.
So you can only sample locally. That's the idea.
I can only...
You're basically using this as a sampling strategy?
Yes, I will.
But you,
Yeah.
okay.
Yeah. I haven't really described this. These are the probabilities that feature in the backward equation for this system, which I was gonna skip. But I can write actually the equation itself and not solve it. So because maybe it will help. So because you start not where you want to be, so you're not there. So the probability in 0 steps is 0. The probability in 1 step is this. Okay, so this is something that's called the backward equation. It doesn't really matter what we call it. But this has to do with the fact that if you want to write, you know, something that takes L steps, then you write the same quantity for L minus 1 steps times the jump probabilities. So you often do this on networks and continuous systems as well. You know, there are two ways to study stochastic systems. One, you can go forward, and that's Fokker-Planck equation, for example. And this one is sort of the backwards, where you think what happens at L, something must have happened at L minus 1, times I multiply by jump probabilities, and then I count. It's like summing over all paths recursively. Right, because this is a sum over all paths that take you from I to j, let's say. And then another step is just another sum over jump probabilities.
But here j should be in S8 in the first probability.
So this one, you can either extend Pij. So usually these things are done for just one step away. Actually, that's a very good point. I was going to gloss over it. So as written, it is one step off the target. You can indeed extend it, you know, and say, okay, this is 0 edge weights, and then you can start from anywhere. But the formula that I'm getting at is only going to work for when you start at the target, you jump one step, and then you travel back to the target, and then you do it over and over again, the so-called return time, so the return process. In which case, this works as written without trying to extend it with zeros, but this has to be one step off. Okay, so it's a process where formally you start here already, and then you must jump off, right? Because otherwise you don't have any dynamics. So you are now one step away, but then from here you are free to do whatever you want. But once you come back, you record the number. Okay, so you return. So Sx is a single node here. So you just return several times, you know, come back several times and record the result. So what's interesting about this is that you can solve this equation by doing a so-called Laplace transform. And this is the stuff that I have to skip for the interest of time. So after, let's say, 3 pages of calculation, you get the following formula. So you first do the Laplace transform, and then you get the first moment. So let me describe all these quantities. So this is called and if I may say so, homework. This is actually in the literature. Some people from France have gone over it recently. So what is this? So this is something that these are the probabilities of making steps L. This is the first moment, which is an average of coming back to any node in X. Okay, so the system is very simple. So here, the set is a single node. So you walk around, and sometimes you come back after 2 steps, right? Sometimes it takes 5 steps because you got stuck in this triangle. Sometimes, infrequently, it may even take 20 steps on this tiny network because you always make the wrong jumps. So you in your simulation, you record it a bunch of times, and then you average over it, and then this formula tells you that this average that you do just by running random walks is 1 over the steady state. So this is steady state probability for occupancy of nodes on Sx. Okay, so instead of doing a simulation, I can solve my master equation, and I can get Pi, if this is I. And suppose, under some dynamics, it may be just 1 over the number of nodes. It may be easier to compute. And then 1 over that, there is no sum because this is a single node. 1 over that is the mean number of steps. When you start from here, then you walk off, and then you come back. So that's nice, right? Because I can compute something that doesn't even require equilibrium based on equilibrium or steady state probabilities. But it's kind of useless computationally because just because this thing requires equilibrium, and therefore you need to walk your network many times, unless you somehow can compute it a priori. And if you don't know the network, which is what I've advertised, you cannot, right? Then you cannot compute this. To estimate it, naively, you would have to walk over the entire network until your probabilities settle down and don't change anymore, don't depend on the initial condition. And then you could say, okay, 1 over this is this, but then by that time I could have estimated this directly on a computer. So the point of this talk, and it's segueing into our work, is to use this kind of approach to make useful calculations. So this is the starting point, this formula. So remember that we had symmetric weights, omega ji equals omega ij, and remember, I worked out pi sub I for symmetric weights, and that was just omega ji divided by omega I. So this part is basically just pi sub I, and this is summed as the formula requires me to do over all pieces in the set, over all nodes in the set. And this is what I call the total outward rate. This is the sum over omega ji summed over all nearest neighbors. So I'm just writing out, I'm basically dividing and multiplying by n.
Sorry, we lost the statement on omega ij.
This one?
And what about? And I lost.
Oh, sorry, ji. this is symmetric weights. If the probability, not probability, the weight is 1, then back is 1 as well. So it's just, the other one is true too. Always true. Okay. All right, so I hope you are still with me because I wrote what this is. This is pi I. And then I'm just writing it out, and then I'm saying that this is omega x, and this is omega, so this is an average over all nodes, and this is an average over of this outward rates over nodes in your set. And then px is diffraction. So we can look at this if, for a simple example, just to make it more easily understandable. So suppose you have a homogeneous unweighted network, okay? Homogeneous means that everybody has the same number of links. Okay, something like this. It's a lattice, if you will. Well, a lattice would have border effects, but you know what I mean, right? So for this node, there are 4 links, and that's it. So then, pi I at steady state, you can easily see from my formulas it's just 1 over n, where n is the number of nodes. And let's say it's unweighted. So all the probability, the probabilities are 1/4 and the weights are 1. So omega I is k and is equal 4 in this example. Okay, and in this case, this average is equal to this average because they don't change. It doesn't matter what's your set of, whether you average over your set of targets or whether you average over all nodes, and you get an interesting result. Lx is n over nx. Okay, so if nx is 1, then you need order n. You need to visit, on average, the entire network, right? Because n is the size of the network. But what's interesting is that if you assign not a single node, but 2 nodes, let's say this is going to be n over 2, because you go back not to the same node, but you make transitions from any node in Sx to any node in Sx, right? So this gets cut down by a factor which is 1 over the number of targets. And this is sort of a central idea, one of the central ideas that we will use to do useful things. So in this particular case, what you would like, so you're sort of halfway there, what you would like is maybe to get px, right, the fraction of smokers. But you have all these auxiliary terms, and they're sort of still in the way. So let's see.
What is that equation at the very bottom of that thing you just wrote there?
This one?
Yeah, WI.
Oh, so k is the total number of links. Yeah, often people use little k's for unweighted networks and capital K. So in this particular example, k is 4 because it's a lattice with four neighbors. Sorry, this was just the example. So, and number of links per node, which is 4 just in this example. So it's always easier to think of unweighted networks. So, okay, we have the first moment, which is given by these formulas. But what we really need to do, so what I want to do is some sort of Bayesian framework, which would allow me to make consistent predictions. So all I have is the first moment. The trick with Cox formula doesn't work on a second moment and higher order moments. Yes?
Can I ask?
Sure.
Is the ensemble you're interested in just the ensemble where everybody starts from? Like, it can be totally out of equilibrium where everybody starts from the same point?
Yeah, it doesn't have to start from the same. Yeah, I mean, it's out of equilibrium. I'm interested in strongly non-equilibrium systems. Otherwise, you have to walk the entire network, and you will get information about it, but it's gonna cost you. You might as well just store it on your computer. So it's short random walks, which means strongly non-equilibrium systems, and you can start your random walks from the same node, from one of the target nodes, and then you must jump off, or you can start from different target nodes and jump them off. On a computer. For example, you would start here, it's actually a single random walk thing. So you would jump here, and then you would start recording your statistics.
But if you start from a point that's really far away from your target set, then wouldn't you expect L to be the average time
Yeah.
longer?
Yeah. So you don't start away. So you start here, and then you jump off. Otherwise, you're already at the target. So this is the return times I'm talking about. But if no one tells me not to do this specific thing, I could start here. Then you're 2 steps away, right? And then there will be an effect, which is a weak effect in many networks. Let me, perhaps I can tell you more later. There are people who have worked out the distance dependence, and it goes away in many networks of practical interest. But still, it's an excellent question, because we started with something like this, and it's not as good as starting off on target and then jumping off, because you don't have this sort of short distance effects. Okay, so but a less elegant framework would have made me start, let's say, always 2 steps away, account for it, and then you could do the rest, which is what we sort of did in the beginning, but then we abandoned it. So a key assumption here, which is sort of the least mathematical, if you will, is that you give me Lx, and you cannot really compute something higher order. But it turns out, so this is this delta L, this is the number of steps between subsequent visits to Sx, okay? So you do what we've just discussed, and you do it many times, let's say with a single random walker, and then you just record how many steps it took me. It's a random number, right? So sometimes it's 5, sometimes it's 7. And it turns out, but that's not a mathematically rigorous statement, that the true So let's say I want to plot it from a numerical simulation. So it turns out that it often, or typically, looks like this. So it's driven by all the eigenvalues of the transition matrix. If you don't have the network, it's huge. You don't have the transition matrix, so that's a problem. So you can never compute this easily. But because only the largest eigenvalue survives when delta L is large, it's actually exponential for the most part. And sometimes it's pretty exponential, even when delta L is not too large. So this is our exponential ansatz. So basically, I computed this somehow, or I talked about it at least, and now I'm using it to make P delta L, which is just an exponential distribution. So now we only have a few steps. There's my eraser. So now we need to write down the probability for the system with several visits. Okay, so what I'm imagining is you started your single random walk as described, one step off target. And then you took L1 and you found the target, or any of the targets in your set. Then again at L2 you found again. So once you find the target, you get absorbed, but all that means that you move one step off the target and you start again. Right? So L3 and then L4, and then you didn't find anything when you had to stop. So you've run L steps. And in this example, let's say you found the target at this, after these numbers of steps 4 times. Okay, so I know what the probability is for each one of these intervals, and I need to work out the probability, for this process with several events. So, but first let me define the inverse. You will see it's more practical. So I've talked about the mean number of steps to return to targets. And let me define the inverse of it, and then I will call it a hitting rate. Okay. So 1 over number of steps is like a rate. So let me just do that. And okay, I shouldn't probably. So suppose this is a single configuration. So this one is delta L1, perhaps minus 1. This one is delta L2. And delta L's are distributed like this. This one is delta L3. So this goes over the entire interval. So probability of a single configuration is going to be the first exponential, delta L1 minus 1. And so on for all the events. Okay, but then in the end you have the probability of failure. So let's say Kx, capital Kx is the number of times you found any target in your set. So number of targets found. And you can find the same target multiple times. If there's a single target, you could have found it in this process 4 times. It's fine. It's not like you throw it away afterwards. So this minus 1 accounts for the fact that you've had delta L minus 1 failures and then a success. You found the target. Okay, you can see it a bit clearer if I rewrite this. So suppose this one is large, that's my limit, and then this one is small, much less than 1. Okay, then I can just expand the exponent. So Qx much less than 1. So then all I did, I expanded this in Qx, right? This is e to the minus Qx delta L. And then I expand and I retain 2 first terms. And now this is a geometric distribution. This is the delta L failures, right? Geometric distribution accounts for, there's a probability of failure and a probability of success. And this is delta L failures. So this would be like P to the delta L. And this is 1 minus P. Okay, and then a success in the end. Okay, but then that's what I meant when I talked about it's actually off by 1, if that's what you wanted to ask. Yeah.
I didn't get where you got the formula for the probability for a single configuration.
So a probability for a single interval is given by this formula, right? So I'm just multiplying because I've seen the target 4 times. And once you found the target, you have to start the formula again. So this term is just this formula for delta L1 minus 1. Okay, in my analogy here, this actually takes delta L plus 1, so it's off by 1. But it doesn't matter because rates are low and delta L is huge. And then times another one, and then in the end, this is the probability of failure. For the rest of the for the rest of the interval, you haven't found anything. You can see it from here. So what is the probability? This is the probability of success. It's delta L failures times success. If there was no success, it would be like this, which is approximately just the exponent. So that's all. So that's the last exponent. And the point here is that all of these things, Qx and the sum over delta Li, it cancels with all these exponents.
So we just to be clear, like the subset x, Sx, where we're interested in
Yeah.
the example would be like the amount of smokers.
Yeah. For example, Sx is the all nodes of people who smoke in Paris. And you don't know, and I walk by the network of friends. Yeah, exactly. And delta L's are from smoker to smoker. So I walk and he says yes, and then no, 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 well, hopefully. And then yes again, so that was 3 steps. So delta L1 is 3. But doesn't have to be the same smoker, right? It could be, but it's just from any smoker to any smoker in that example. Okay, so the point here is, I should have mentioned before I ran out of time, okay, let me write. So when I multiply all these factors, all these exponential factors, I get basically a prefactor of qx to kx. Kx, remember, is the number of smokers I found in this process, times some sort of exponent, which is like this, and this is basically e to the minus qxl. So now, I should mention before I run out of time that this is published in this paper, so I'll leave it in a corner. But of course, there are no details. So this is a PRL that came out this August. Okay. But as you know, PRL is 4 pages and details are missing. Okay, so this is for a single configuration, but of course I need to sum over all configurations, or I want to sum over all configurations that result in the same number of targets. So P, now we're getting closer to something. So probability of Kx given Qx is this single configuration probability times a factor that's combinatorial factor that sums over all configurations. And here is a nice surprise. Remember that Kx is much less than L, so this is consistent with the rates being low. Okay, so strictly speaking, this is not going to work when your subset is 80% of the network. Oh, you're pushing your luck anyway. So, but when Kx is much less than L, and that means that you run, and then you find a smoker, then you run again for a few steps, at least for a few steps, and you find a smoker. For this process, I was able to, for example, approximate L minus Kx by L and make other approximations. And the exponential ansatz is the one that works better when you have relatively many steps between events. And what I was gonna say. So sorry, first I need to. I will rewrite it. So this can be simplified like this when kx is much less than L. So what we get in the end, and all I did, I've summed over a bunch of exponential probabilities, is that the probability to have kx events, kx target finding events, given the rate, is given by the Poisson distribution. And this is actually not surprising at all, because that's where these distributions come up when you have a single rate, right? You have an exponential rate. Things come with a certain rate, so you kind of expect a Poisson distribution. But it was derived here and not in the usual Poisson limit, and slightly different limit. But still, you expect Poisson. So we're almost done. So we have something that's the inverse of what we want. We want some pieces of Qx to be estimated. And we have given Qx, right? We have a probability of the number of target finding events. So, but we need to flip it, right? So what we want is this. So this is the probability of a model given the data, and this is just a flip in a Bayesian sense. Okay, so this is the likelihood, and this is the posterior probability. Now the Bayesian part comes in. But it's very easy to do the Bayesian part because you assume uniform prior. So you need, now you think of things as a function of Q, right? Here Q was given, and K is sort of what you estimate. Now K is given, which is your counts, and what you're estimating is Q, so your normalizations should involve Q. And the way Bayesian formula works, it's a likelihood times prior divided by the normalization factor, which is called evidence. But if you have a uniform prior for Qx, so before I take data, I don't know anything about Q. Q is a rate, so I do know that it should be between 0 and 1, right? If you look at the formula, it's like proportional for unweighted network to nx over n, so nx could be 0 or n. Of course, when it's closer to n, the whole thing will kind of break. But in principle, the prior probability, so should be, you know, it's a nice model for it is a uniform prior, and then it's nothing at all because it's 1 over 1. So what we have is Qx, Kx, Qx over L. And then this cancels as a function, because it's not a function of Q. But then I need to normalize, which is what people call evidence in a Bayesian sense. But all I'm doing here, I'm taking this piece, which is the only piece that's Q dependent, and I'm normalizing it by taking the integral between 0 and 1. So now, people know very well what the posterior probabilities are for the Poisson process. So this is the so-called gamma distribution. Okay, so under some conditions that I'm sort of glossing over a little bit, but to very high precision. So this is L, the total number of steps in your process, right? So L steps in random walk. the probability to be to have a rate qx, which remember consists of the fraction of nodes with property x and a few other things, is just this. So kx you measure in your random walk, L you know because you set out to take 10,000 steps, for example. So you have everything. And what's nice about this gamma is that it very quickly becomes Gaussian. So gamma distribution has a bit of a tail. So its mean is not its maximum likelihood value. But for all practical purposes, we can skx, the number of times you found the target goes up. It actually becomes Gaussian. P qx given k of x. And its mean, because Gaussian is symmetric, is its maximum likelihood, right? So I'm talking now about a Gaussian. So that's the maximum likelihood value, and that's the same as the average value, right? Because it's symmetric. And this is completely to be expected, right? Because this is basically the rate is the number of events divided by the total length of the trajectory, right? Or in other words, the average, the inverse of this is the number of steps between events. And between events, it's just going to be L divided by the, if I make 10,000 steps and I find the target 5 times, it's 10,000 divided by 5, 2,000 per target finding event. So this is completely to be expected. And the other thing you need for the Gaussian is the sigma. And it's given by this value divided by the square root of kx. So this is true for any Gaussian. So now I have everything to given the data, which is my number of counts, and also L, right? Number of random walk steps. I can estimate the rate, but the rate you don't really need. You would like to estimate the fraction, for example. You don't want qx. You want px, which is, remember, was nx over n. And for this, it's a little bit awkward. So I know how to do this, but I don't really know how to do this, guys. That's the average of the, for unweighted networks, number of links, or what I call the average of the total. So average of the total outward rate, sum over all neighbors. Over all nodes in set X, and this is over the entire network. So, if my nodes, target nodes that I designated have 3 links, it's unweighted network, 3 links and 4 links, then this would be 3 plus 4 divided by 2. But this has to do with the entire network, so it seems to be not practical. Well, you can impose. So let's talk first about. So we have the whole distribution, but let's talk about the maximum likelihood value for this, okay? So I want to impose that the sum of these maximum likelihood values, it's a very interesting system. So your P of x is your predicted probabilities of property x. So they sum to 1, but they're all random numbers. So usually you're used probably to some probability distribution like this, right? And it sums to 1, given by a histogram. Here, I don't unfortunately have an exact value, I have a Gaussian estimate, but I can tell you that this one is px5, let's say, maximum likelihood plus minus sigma px5. So you see it's the probability distribution that has uncertainty in it. In other words, it's a posterior probability estimate for a probability. So I can focus on its maximum likelihood value, and then it's not a distribution. And this is exactly what I can do. Yep. Okay, so if to focus on the maximum likelihood value, all I have to do is put hats on it. And then I can say this sums to 1, so this awkward term will disappear, but these ones will stay. And this kx, remember, was, or qx hat was just kx over L. So 1 over L will drop out, but kx will stay. Okay, so in fact, I don't know this perfectly, but I do know, px hat should be the same bars, and then each one is just a bar, right? So now we don't worry about the fact that this has uncertainty anymore, right? So it's a regular probability distribution. It sums to 1, but it still has this omega, and this omega should be there because for a non-uniform network, actually, imagine a network with hubs. So these often occur in nature. Okay, so you have strongly connected hubs once in a while, and then once you do a random walk, you come to these hubs all the time. That's just a fact, from a simulation. And to account for this fact, you need to divide out the weight of the hubs. So the unweighted estimate actually should have this 1 over omega, and people knew that before.
I have a question. What does your original exponential distribution for the delta L imply? Does this imply that all the nodes with property X are randomly distributed, or are they allowed to cluster somehow?
No, it doesn't impose restrictions like this. All networks clustered with communities, almost disjoint, will be exponential eventually. Because the way to see it is to imagine a network and a transition matrix for the entire network. Then you diagonalize it, and you will have eigenvalues which you can sort. And then the lowest eigenvalue is the one that stays as delta L grows. So it's always exponential in the tail. But the question is, how good of a fit is it? I'm fitting an exponent to something non-exponential, which in this intermediate regime, if the second eigenvalue is almost like the first eigenvalue, can be kind of large. So part of the message is that it works despite this sort of crude ansatz. So I can
Can you somehow quantify how much of the distribution is in this first part and how much is in this tail? Somehow by saying of how these X properties cluster somehow?
So clustering is, yeah, you can P of delta L is something that we always assemble. It's as we do random walks, and I have examples of these probabilities. Perhaps I can show you. I can just show you what it looks like on a real system. I was gonna do it later anyway. So this is just a talk, and yeah, here we go. So this is for Erdős-Rényi, which is a random network, where you just basically put down 1,000,000 nodes, then you designate 1,000 targets randomly, and then you compute the statistics of P delta L. And for this particular one, you see the exponential fit works quite well. So you could say it's not fair because it's a random network, but it's actually true for all the examples we've looked at. Although when delta L is small, you have deviations sometimes. It actually doesn't throw off your predictions. So.
Then from here, the fraction of the target is quite small compared to the total network. When does this break down in terms of the ratio?
Right, right. So if your fraction of targets is close to 1, then things might start breaking. But that's usually the limit you want. And I'm going to explain it shortly. I didn't even get to sort of saying why that's the case. So this is actually, believe it or not, but this is a trivial case where you just estimate probability over property, which might or might not be abundant. And if this is smokers, non-smokers, and you have 80% of smokers, the framework might fail. Okay, because you're sampling from the non-exponential part of the distribution. I mean, here it works, but imagine that because it's pretty exponential all the way, but imagine that your delta L's are always between 0 and 1,000. Then you would be in a regime where the green line is not quite like the blue bars, right? And then that could accumulate error. But part of the message here is that it doesn't. We've tested it on many systems and it's quite robust. But there's always room for improvement in principle. In principle, this is very simple. It's sort of hidden by these details. There is a Poisson for target finding, which is kind of random, right? Then you invert it into posterior, which is a standard step. And then you infer your properties. But it works. OK, so let me, because we don't have that much time. So I told you how to sort of estimate probabilities of a property, but you still don't know. You need an estimator for this omega, because you don't know in advance, right? This would be like the average number of friends per smoker in your set. But there is a trick that you can use. You can say that your property X is your outward rate itself, the number of links, okay? And then there is no average, and you know what the number of links is exactly. So this sums over all the bins. So this is a continuous number, but you make it into NW bins. So if this is true, this must be true, but omega x is not an average because I subdivided all nodes by their rates, and therefore the average is the number itself, because that's how I subdivided. So finally, here is a practical formula for doing all statistics on the network. So don't use this one because you don't know how you get this, but you don't know how to estimate this. When you get to the node, you know its outward rate, right? If you don't know, then this won't work. Remember, this curly NW is the number of bins that I binned my rates in. If rates are the number of links, then it's naturally binned, right? You can do like 1, 2, 3, up to some maximum. That's it. So to estimate at least maximum likelihood estimate, and there is a sigma as well, but the maximum likelihood estimate of any property is that when you come to a node, you record the property of interest, smoker, non-smoker, but also you record the number of friends, okay? And then you just run a matrix. It's a two-dimensional object, right? So on the x-axis is x, on the y-axis is omega, which is the number of links. So you know this for every node, and you just build your statistics this way. That's it. So all you have to do is to do this random walk and compute these numbers. This number is just the sum of this number over x's. So basically you run a table. You know what your bins are, and you get the maximum likelihood estimate, and you get the sigma as well, and I told you it's Gaussian. And it's divided to unbias the estimate. So this has to be there, and people have talked about this before. So for example, you can do first order moment. So x average would be this, but I don't know px. We've discussed this, right? I only know its maximum likelihood estimate plus minus sigma. Well, so I can compute something like this with maximum likelihood probabilities. So I can do this for sigma and so on. Let me skip this in the interest of time and tell you, and that's the most surprising thing. So all of this, believe it or not, is sort of not surprising, right? So you do your counts, you walk around, you do your counts according to the prescription of x and w, and then you divide out the statistics to unbias it, and that's it. So this derivation goes through the Bayesian framework, but people have done something like this before. But what's surprising is that I can do the following. So I can estimate not only the fraction of smokers, which would be this, but the total number of smokers on the basis of a small non-equilibrium sample. Okay, so again, so there are 5 million people, 1 million of them are smokers. I can ask 10,000 people, and I will have a very good estimate of the total number, not fraction, but number of smokers. So how does that work? So this is the next, sort of the last mathematical step. Well, along the same lines, so if I can divide things into x subsets, I can just designate what we call, I can divide nodes into two classes, what we call pseudo-targets, because I just chose them. They're not real targets, they're pseudo-targets, and the rest. So this is what this was. You know, I chose 1,000 pseudo-targets by just by randomly. They shouldn't be all bunched together, although this doesn't seem to be a big problem. So basically, you just designate some targets. So, and say NP is the number of pseudo-targets. Let me call them PT, pseudo-targets. And then, of course, because you've designated them by hand, you know this, right? So you know that you chose, 5 nodes with 4 links and 5 nodes with 2 links. So you know this known. So the rate to go to pseudo-targets from my main formula, written in terms of pseudo-targets, P stands for pseudo-targets, okay, not PT but P, is this. So I know how to estimate rates. I know this because I choose it. I know this because I choose it. I just don't know this and this. This I don't want, but I can get rid of it. And this is what I want. It's n, the total number of nodes. So we can just write out an ugly probability, posterior probability. Which unfortunately is not as nice as a Poisson or anything like this. But it just comes from what I already told you. It's again this exponent. It's basically a gamma distribution where instead of QP, so for QP it's a gamma, but now I'm substituting this, so I'm getting something uglier. And then again, uniform prior. Basically what this means is that You can do a continuous thing and not worry about ugly sums. So NP is the lowest in my estimate, right? Because if I already designated NP, the size of the network is at least NP. The upper limit is infinity. Nothing depends on it, so you could put n max and then go n max to infinity. So, and the integral, you know, the expression is this expression. Okay, so all I've done, I've taken the gamma distribution and I rewrote this. But now it's a posterior probability for n. And it's ugly, right? Because it's e to the 1 over n. So I don't know the name for this distribution, right? So this particular, you know, it's basically 1 over n kp e to the minus alpha over n, where alpha is everything except n. But it turns out that it also quickly becomes Gaussian. So you can get its mean, which is its maximum likelihood, you know, the center of the Gaussian. And then actually, let me sort of be quick here. You don't know this, but you can estimate it through your counts. And I'm skipping a step where you estimated this. So all you need to do, you need to assemble the counts for W's, you know, for the binned rates, or for the number of links. This you know, this is what you're recording. And you can compute the whole thing. And sigma and can be worked out approximately. So it's not quite a Gaussian. But to the first order in Kp. So if Kp is like 5, 7, 10, the next order is going to be, you know, 10 squared. So it's a small. So by an explicit calculation, you can work out. So if you have this, divide by Kp. Sorry, this is squared, of course. It's always a square. Well, if there is no square here, sorry, this. N over k, square root of Kp is sigma, and then sigma squared is this. So now, and actually we're doing well on time, this is the whole framework. You can, from a short simulation, get anything you want about the network, and you can get the size of any subset or the size of the network from short random walks. So let me show you a few things of how it works here. So this is again a random network. So the green line is the P of the degree distribution, you know, the true degree distribution for this network that we've simulated, you know, just made on a computer. The red dots is our guesses, and the mean, you know, there are two lines, the dashed line and the solid line, and this is the predicted and the exact mean. Okay, so it just works. You could say, okay, it only works for Erdős-Rényi, and that's not true, obviously. Otherwise, it wouldn't be a PRL. You can do this for Wikipedia. Yeah, how about this? So Wikipedia, you can do a web crawler, and you can go from page to page. So your nodes are Wikipedia pages, and on the bottom of each Wikipedia page, you have links to other pages. So they're directed, you go from A to B, but you can turn them into undirected because you can do whatever you want, right, within reason. So you make them unweighted, undirected, then you walk this network using a web crawler, and you visit, so you designate about 5,000, you visit Wikipedia you make 50,000 steps, okay? And then you get the size, and This is the posterior, as you collect statistics, KP. And it converges to something that you can look up in the Wikipedia stats page. And this is for the size, but we've computed many, there's a table in the paper, and it's right on, right, for all the numbers that we were able to find, because sometimes the numbers are a bit out of date or with images, without images. So we can compute, for example, the average size or the distribution of sizes of Wikipedia pages, because each page has a size, written somewhere. Average number of links, the size of the Wikipedia itself. This is the size of the English language segment of it. So what else can we do? We can track epidemics. I'm not going to be able to go into this, but I can show you one slide. So there are models that people use to model epidemics, right? So there's a so-called SIR model, when you get infected, susceptible infected, and then they're covered. So this model has a phase transition, and it means that at some point, the disease dies off, but then above a certain threshold, the disease stays and takes over a finite fraction of the population. So imagine, this model is too complicated for me to describe. It also involves like actual interactions between people, but there is a network underlying, sort of people interaction network underlying disease epidemics. And as in our simulation disease spreads, we track it by just asking people, are you sick or not sick? Right? And then the actual dynamics is the blue line, and then our predictions are the red dots, and they're a little bit off because the disease sets in quite fast. And you sort of, by the time you ask, it depends, of course, it's all simulated, but the time scale of asking and the time scale of disease development, and if those are not sufficiently small, tau ask by tau develop disease, then by the time you ask, things change a little and it lags. But in a simulation, of course, you could get rid of it. So you can also do this kind of thing, which is, I think, the last thing I will tell you about. Okay, so it occurred to me later on, after we worked all this out, that if you can do networks, you can do random sampling as well, because random sampling is exactly like an unweighted network, which is called complete. You can jump from somebody to someone else. And random without replacement has little loops on it that, that means that you can sample yourself twice, right? So in this case, and this is funny because I didn't know any of this. And turns out people work on it, and it matches. So with all the math that I've done, it's very easy to deal with the complete network that's unweighted, and each weight is 1 over n. This is Wji shown there, and my formulas, which are right here. So for this network, this is equal to this, right? Because the average over targets or pseudo-targets is the same as this. So it's ln p over kp. And then it turns out that there are people who capture animals, tag animals, and then they recapture them. And they need to estimate population sizes. So there is a whole field, which I discovered by accident. So this turns out to be, in this particular case, the so-called Lincoln-Patterson estimator of population sizes. And the way it works is like this. So what is set a pseudo-target, right? So how does a biologist set a pseudo-target? So there is a cage. And being a physicist, that's my animal. Okay? And then you capture animals, and then you tag all of them, right, somehow. Put a ring on a crow, something like that. This is day 1. This is called mark. And then next day, you set out your traps again. So day 2. So these were all marked. And suppose you got 6 or 7 things, and 2 of them are marked. Okay, 2 of them had rings. So now this is enough information to estimate this, because in this language, n is the number of animals, the one that you want to estimate. And p, which is 5 here, is the number of animals you marked. L, if you think about it, this is 7, is the number of animals captured on the second visit. So this is the size of your sample. So this is setting the pseudo targets, and this is my random walk, my random sample of size 7. Number of animals captured day 2. And Kp is equal to 2, because this is the number of marked animals. Number of marked animals A captured. Okay, so we can estimate. Let's see if it's a. So L was 7, and P was 5, and Kp was 2. So unfortunately, it's not a round number. It's 35 by 2, but you could say it's approximately 17, right? Because you have to have a round number. I was hoping for a round number. But okay, so, and of course it makes sense, right? Because if you marked only 5, and 2 of them were captured in such a small sample, then the population must be small, right? It's sort of, this formula sort of makes sense. So what we've done a Bayesian framework for it, right? So usually people just tried this. But there's also one more difference here, and that is people focus in biology mostly on sampling without replacement. Okay, so it's which for our limit, when sort of Kp is large and the rates are small, doesn't matter. But for a biologist trying to estimate a small population, this is really a small sample size, and you cannot do the Gaussian approximation that I focus so much on, right? So, but in fact, you don't have to do it like this, right? So this is sampling without replacement. That's the problem, right? Because if you capture this guy, you're not going to sample for it in a population again. So the framework doesn't work, but well, it works in a certain limit, right? When this number of A captured is large, and when the sample is large enough, L large, and Kp is much less but large. But in fact, you don't need it. You don't need to bend the experiment to framework. You can actually do a new experiment, it occurs to me. You don't have to use cages and do sampling without a placement. All you have to do is to basically take a picture. Right? Take a picture of an animal and see if it's tagged or not, and don't capture and make math complicated. Right? Just let the bugger fly away. Right? And then you will have actually exactly a random walk on the network for which all these things work. Even if you don't make the Gaussian approximation, we have all the mass. Right? So idea is do a different estimator. And the estimator shouldn't be day 1 and day 2 without a placement, but just mark your pseudo targets like this, and then assemble. This is suppose you take pictures of animals. This is unmarked. This is unmarked. This is marked. Unmarked. Unmarked again, and then you don't capture them and hold them. Right? It may be hard for Actually, I was going to say it's maybe hard for crocodiles, but maybe it's even easier to take a picture of crocodiles than like trying to build a giant cage and like capture 7 crocodiles. But continuous observation, and the math works even better for it. So I didn't get, because we're out of time, although I did start 5 minutes late, but I wanted to show you. I will just say what things can be done in a more traditional population genetics, which is sort of what my talk was supposed to be about. So I told you all kinds of things, you know, epidemics, biology, right? And then how to deal with estimating animal populations. But in population genetics, you can have a mutation rate and a population size. And if it's much less than 1, this is the so-called monomorphic limit. And hopefully you'll hear more about this later today in a session. And well, unfortunately, population, you know, with mutation, selection, and stochastic effects that are called genetic drift, it's too difficult. It's not a simple random walk of the type that I described. Okay, so it's coupled random walks, and it's much less tractable. But in this limit, the whole population, because the stochastic effects actually are predominant, a mutation comes in and it fixes or disappears. A mutation comes in and it fixes or disappears. Okay, so the entire population makes a random walk. And in a system, sometimes you can approximate things by saying, okay, this is a sequence network. Each node is a sequence, and edges are mutations. Okay, so it's a sequence network. And let's say this is the good guys that are functional, and most of them are non-functional. And this is actually what some experiments show us, right? So there is this sort of a small fraction, perhaps 1% of functional protein or signaling pathway. And then on the bottom, there's the junk. You know, you make a mutation, and it's not good. So there are connections between planes. But in this monomorphic limit, you only walk the upper plane. So this is high fitness. This is low fitness. And you can never take your entire population to the lower plane. So it's there in a sense that the number of links is not uniform anymore, right? There could be highly connected nodes and the nodes that are disconnected or less connected. And if you want to estimate the size, let's say, of this functional space, you can do it using this technique. So there is one important difference. There are waiting times. So what I showed you is simple random walks in the sense that you have to jump. Here you don't have to jump, because if you make a bad mutation, you just stay at this node. This individual dies, right? But it's a very simple extension of the formulas, and turns out let me write it here, that you get this for the initial remember, that's how it all started. Then I did the exponential ansatz, then I did the probability of a single configuration that I multiplied by the number of configurations, did the posterior. So here I had, it was W, but for unweighted networks. So it's an unweighted network here because this is a two-plane system. And you can mutate to here or to here with equal probability. But you also can stay, right? So there's like a trial per generation, and then you stay or go, and then you can work out all these rates. And this capital R is the total number of mutations per node. And for example, if you're mutating DNA, it would be 3 times the length of the DNA piece, right? This is the total number of single point mutations that you can make from a sequence to sequence, right? Because you don't mutate into itself, so it's 3, and then you can mutate any site, 3L. So it would be like this. And that's it. So this is an unweighted network otherwise, right? I'm only talking about the upper plane. So it's not W's, but K's, the number of links. And this formula is almost exactly the same. Let me just write it side by side for the unweighted network on a simple random walk. So what I worked out for you a little while ago, I wrote it in terms of weights for weighted networks, weighted undirected networks. But if I replaced W by K, I would have this, and this is even simpler. Remember, I had to estimate this sometimes. It involved some counts. This is a constant. So I can use this as a starting point instead of this, and the rest of the procedure just works. Now, it's not very practical because you have to walk around and assemble your statistics and to estimate the size of the upper plane. This may acquire more mutations than one would like to make in the monomorphic limit. But at least as an idea, I think that's fine. And if the only other thing I want to say is that this comes from so-called continuous time random walks. So this procedure works not only for simple random walks, but for random walks with waiting times at nodes. Okay, and that's nice because it's a larger class of networks. So you don't have to jump each step. You can wait and jump with some probability and then stay with some probability to stay. And the framework carries through. Therefore, you can do your estimates. So this is one such example. Maybe it's not such a good one because you need to walk the upper plane in the monomorphic limit, which is hard to do experimentally. But at least it gives you maybe an approach that's potentially useful. All right, so that's it. And I think I'm out of time. So I'd like to acknowledge my student, Willow, who has worked out this framework with me and did all the simulations. All right, thank you.